Hello everyone, this is a lesson summary of lesson 7.5 compound events. So first of all, let us understand what are compound events. To understand compound events, first of all, let's describe what's a simple event. A simple event is an event that describes a single outcome. A single outcome. For example, when you are tossing a coin, the probability of getting heads is a simple event. So it will be 1 over 2. A compound event is an event made up of two or more simple events. So a compound event by definition is an event that is made up of two or more simple events. Under compound events, there are two types of events under compound events: mutually exclusive events and mutually inclusive events. So first of all, let us discuss what's mutually exclusive events. Events that cannot both occur in the same trial of an experiment. So something like when there are two events that cannot happen at the same time in the same trial of the experiment. Okay, for example, rolling the number 1 and number 2 on the same roll of a number cube. So in one roll, I can only get one number. I cannot get two different numbers at the same time. So rolling number 1 and rolling number 2 are mutually exclusive. They are exclusive events because they cannot occur at the same time. So when we represent mutually exclusive events using a Venn diagram, this is how we represent as shown in the picture below. So event A and event B are completely separated without having anything in common. There is nothing common in between them. So they are totally separate events. This is mutually exclusive events. The probability of two mutually exclusive events A or B occurring is the sum of their individual probabilities. So to calculate the probability of two mutually exclusive events A or B, so it can be either A or B. It cannot happen A and B at the same time. It should be either A or B that will occur. So to calculate their probability, we add the individual probabilities of each event as shown here. Probability of A union B. So this symbol is known as union, as I think you already know. Okay, it is also indicating or. So union means or. A union B, or we can read in general A or B, is equal to probability of A plus probability of B. The example given here is very simple to understand. Probability of a number less than 3 when you are rolling a number cube. So probability of getting a number less than 3, which is there are two numbers less than 3, 1 or 2. So probability of getting the number 1 or getting the number 2. We cannot get them at the same time. It's or situation. So I can only get either the number 1 or the number 2. So what's probability of getting the number 1? 1 over 6. What's the probability of getting the number 2? Again 1 over 6. I add their individual probabilities, I'll get 2 over 6, which is, if I simplify, I will get 1 over 3. This is a simple example for understanding mutually exclusive events. Now let's solve an example question. A group of students is donating blood during a blood drive. A student has a 9 out of 20 probability of having the type O blood and a 2 over 5 probability of having the type A blood. So 9 over 20 for type O blood and 2 over 5 for type A blood. Explain why the events type O and type A blood are mutually exclusive. So first of all, we need to explain why the events are mutually exclusive events. So the it's really simple to understand that a single person cannot have two different types of bloods at the same time. So a person can either have type O blood or type A blood. He cannot have type O and A at the same time. That's why the two events are mutually exclusive. That means both of them cannot exist in the same person at the same time. Okay, so a person can only have one blood type. Now, what is the probability that a student has type O or type A blood? So what is the probability that a student has type O or type A blood? The word here is or. So we know that it is, so type O is, let's say, the event A, and type A is our event B. And then we have the word or. Or means we will use union. So probability of A union B. That means I just simply have to add their individual probabilities. So probability of type O union type A equal probability of type O plus probability of type A. The probability of type O is given here 9 over 20, and probability of type A is given here 2 over 5. Just add them and the answer is 17 over 20. Let's solve one more question. Each student cast one vote for senior class president. One of the students, of the students, 25% voted for Hunt, 20% for Klein, and 55% for Viola. A student from the senior class is selected at random. First of all, explain why the events voted for Hunt, voted for Klein, and voted for Viola are mutually exclusive. So if we read the question, it says each student cast one vote. So per student, one student can vote only one time. That's why the same student cannot vote for two person, two people at the same time. Same student cannot vote for two people at the same time, and hence the events voting for Hunt or voting for Klein, voting for Viola are mutually exclusive because the same student cannot vote for two people. He or she can vote only one or vote for only one person. Now, what is the probability that a student voted for Klein or Viola? So voted for Klein is event A and voted for Viola is event B, and the word used here is or. So we know that it is probability of A union B. So probability of Klein plus probability of Viola. Probability of Klein, it's given, the numbers are given in percentage, so we can just directly use as percentage. So for Klein, it was 20%, and for Viola, it was 55%. Just add their probabilities, 20 plus 55, which is 75%. Coming to inclusive events. Inclusive events are events that have one or more outcomes in common. That means they have one or more outcomes. The two events have one or more outcomes in common. So it's given here an example. When you roll a number cube, the outcomes of rolling an even number, and rolling a prime number are not mutually exclusive because the number 2 is both a prime number and an even number. So the two events are not mutually exclusive. These are the two events. Rolling an even number is event A, and rolling a prime number is event B. Okay, but they are not mutually exclusive because they have something in common, which is the number 2. So the events are inclusive. So to represent using a Venn diagram, we can represent like this. So since the two events are even number and prime number, so the two circles are for two events, okay, and uh, the numbers on the number cube are from 1 to 6, right? So 1 is neither prime nor even, so it's not included anywhere in either of the circles. The numbers we start from 2. I hope you all know that 1 is not a prime number and it is also not an even number. So it's not included in either of the circles. Okay. So the prime numbers are 2, 3, and 5. 2, 3, and 5 are prime numbers, and even numbers are 2, 4, 6. So in both the cases, 2 is common. So that's why this is the common area between the two scenarios. Okay, so they are intersecting each other. Okay, or they are uh, overlapping each other. Okay, the two circles are overlapping, and that is the common area. In the common area here, we have the number 2 because it is both prime and even. So this one, as we know, this symbol, I think you already know from before, is intersection symbol. It's known as an intersection. So it's indicating the common area, the region that is of the two circles that are intersecting or overlapping. We call this as the intersection. Okay, so even numbers intersection prime numbers is the number 2 because it exists in both the circles. It's common. This is mutually inclusive events. So there are three ways, just explanation of the same. Three ways to roll an even number, 2, 4, 6, and there are three ways to roll prime number, 2, 3, 5. The outcome 2 is counted twice when outcomes are added, 3 plus 3. The actual number of ways to roll an even number or a prime number is 3 plus 3 minus 1, because we cannot count the number 2 twice. We have to count, since it is the same number, we only have to count it once. We don't have to count it twice. So we have to remove one of the counting. So it's only the number 4, 6, 2, 3, 5. So there are only 5 numbers, not 6. Okay. So the concept of subtracting the outcomes that are counted twice leads to the following probability formula. So we have a probability formula for these type of cases. The probability of two inclusive events, A or B, occurring is the sum of their individual probabilities minus the probability of both occurring. So event A and event B, if they are inclusive events, we add their individual probabilities and then subtract the probability of both occurring. Means both event A and event B occurring at the same time. Okay, so for two inclusive events A and B, A union B again, okay, A union B. So in the case we did was prime number or even number. Even here it is or. Okay, the situation is still or, but here we have something in common, whereas in mutually exclusive we did not have anything in common. That's the only difference between mutually exclusive and mutually inclusive. Probability of A plus probability of B minus probability of A intersection B. All right. So the example given, when you roll a number cube, probability of even or prime, probability of even plus probability of prime minus probability of even and prime. So the word used here is and is for the symbol intersection. Okay, and that means it should be both, or means it can be either, but and means both conditions should apply to that number. So 3 over 6 plus 3 over 6 minus 1 over 6, which is 5 over 6. Now let's solve an example. Find the probability on a number cube rolling a 4 or an even number. So this is my event A. rolling a 4, or an even number. This is my event B. So A, just a second. This is my event A, and this is my event B. Okay. So as I know, rolling a 4, what's the probability of that? So probability of A would be, rolling a 4 means 1 out of, I mean, 1 out of 6 cases. Sorry. Okay. Rolling a 4. And rolling an even number would be, there are 3 even numbers out of 6. Right? So according to our formula, but as I know here, the number 4 is also an even number. The number 4 is also an even number. So these two events A and B are not exclusive, but they are inclusive, because this, they have something in common. The number 4 is also an even number. So probability of 4 and even also exists. So you can write like this: probability of A union B equals probability of A plus probability of B minus probability of A intersection B, which is probability of A, as we saw here, 1 over 6, plus probability of B is 3 over 6, minus, in this case, since the number is only 4 and even, so here also it is 1 over 6. 4 and even, A and B, A intersection B means 4 and even. How many cases we have for this? Only one, the number 4. The number 4 is the number 4 and it is even, so 1 over 6. So the answer is 3 over 6, which is 1 over 2. Now, this is how the answer goes. All right. Another example, same type. A card is drawn from a deck of 52 cards. So we know that there are total 52 cards in a deck of cards. A card is drawn. Find the probability of the given. Drawing a king or a heart. Drawing a king or a heart. So I know that in the hearts, a hearts card, or in the heart suit, as we say, we have a king card as well. So that means these two events, king or a heart, drawing a king or a heart, this is event A and this is event B, they are not exclusive, because there is a king card in the heart suit. So we know that they have a common area. So the one card is common, right? So first of all, since I know that they are inclusive events, so we can just first do probability of A. How many kings are there? Drawing a king. There are 4 kings out of, there are 4 suits, so in each suit there is 1 king, so 4 kings out of 52 total cards. Probability of B, hearts. How many hearts card are there? There are 13. We know that. So we already learned from the previous lesson the number of cards in each suit. Okay, and there are 4 suits. Each suit has 13 cards. So 13 out of 52, right? And probability of A intersection B. A intersection B means A is king and B is heart. So king and heart. Probability of getting a card which is king and heart. So there is only one card Okay, out of the 52 cards, which is both king and heart. All right, so probability of A plus probability of B minus probability of A intersection B. So let's put the answer. So this 1 over 4 means 13 over 52. If you do 13 over 52 and simplify it, it's 1 over 4, right? So the answer will be 4 over 13. So you can do it the way I showed. This actually means 4 over 52 plus 13 over 52 minus 1 over 52. So 4 plus 13, 17 minus 1, 16 over 52. You try to simplify, cancel both of them with 4. 4 fours are 16 and 4 13s are 52. So the answer is 4 over 13. Right? Let's proceed to example 3. So of 1,560 students surveyed, 840 were seniors and 630 read a daily paper. So first of all, we have to differentiate our events. So seniors is one event and read a daily paper is the other event. So there are two events going on here. 400, total 1,560 students were there. Out of that, 840 students were seniors and 630 of them read a daily paper. The rest of the students were juniors. Now, only 215 of the paper readers were juniors. So 215 of the paper readers were juniors. That means total there were 630 students who were reading the paper. Out of that, 215 were juniors. Out of the 630 who read paper, 215 were juniors. That means the remaining were seniors. What is the probability that a student was a senior or read daily paper? So here, from here, you can identify your event A and B more clearly. So A or B, right? First of all, it's simpler to solve this question by representing them using a Venn diagram. So if I represent this using a Venn diagram, I need to collect all the data from this question. So total there were 1,560 students, right? So there are 1,560 students. Now, definitely they have something, there is a common area between the two events, that is senior and read daily paper. So they said there were 840 seniors. So that means total in the, let's say this is the senior circle. Okay, so seniors and read daily papers. Read daily. Okay. Anyhow, they said 215 of the paper readers were juniors. So read daily paper is this whole circle, but this is a common area for seniors and read daily paper. So the remaining will be the juniors. That means 215 is here. Okay, so if 215 of them were juniors, that means the remaining daily paper readers were the seniors. So there were total 630 paper readers. So 630 minus this 215 who were juniors, I'll get the number 415. So these were seniors and read the daily paper. That means it's the common area, 415. All right. I'll show a clear diagram after the explanation. And then, so there were total 840 seniors. So if 415 are here, that means the remaining should be here. So 840 minus this 415, which is 425, right? Yes, so this is how it is. All right. Now the question is the probability that a student was a senior or read a daily paper. To find that probability, senior means this whole circle. Red daily paper means this whole circle. Okay. So we included the common area as well in that. All right. That means I have to add all the numbers in these two circles, like this one, the middle one, and the last one. Sorry, the diagram is messy. I'll just change it to next slide. So using Venn diagram. So this is better representation. So this is what we got. So total 1,560 were surveyed. These many were seniors. So if you count, if you add these up, you'll get the total number of seniors. And if you add these up, you'll get total number of paper readers. All right. So the question is seniors or paper readers. That means we have to add probability of seniors plus probability of paper readers minus probability of senior and paper readers. When you use Venn diagram, it is much more easier because you can just say add all these three numbers and divide it by the total probability. So your answer should be 1055 over 1560, 211 over 312. But let's see if we get the same answer when we use the general method. That is probability of seniors plus probability of paper readers. Sorry, probability of senior union paper readers. Okay. So probability of senior plus probability of paper readers minus the probability of senior and paper readers. So 1055 over 1560 as I said, and the answer is 0.676. Exactly correct. So it's easier sometimes to directly get your answer from the Venn diagram. But then this is, if you don't understand to use the Venn diagram, you can also use this method. Venn diagrams are for representation, simple representation and understanding. So the probability that the student was a senior or read the daily paper is about 67.6%. So of 160, let's solve another question for more clear understanding. Of 160 beauty spa customers, 96 had a hair styling and 61 had a manicure. There were 28 customers who had only a manicure. What is the probability that a customer had a hair styling or a manicure? So identify your events A, B. Okay. The question is A or B. That means probability of A or B. That means we will use A union B. Now, first of all, represent using the Venn diagram. Total 160. So 96 had hair styling. So 96 did hair styling, and 61 had manicure. There were 28 customers who had only a manicure. That means the remaining had hairstyling as well as manicure. It's in the common area. Total 61 were manicure minus the 28 who did only manicure but no hairstyling. So the 33 would be both hairstyling and manicure. So this is how you'll represent using the Venn diagram. Okay, so as I said, only 28 had only manicure. That means 33 had both hairstyling and manicure, and 63 had only hairstyling. You need to understand how did I get the 63? By subtracting how many were there? 96 did hairstyling. So if 33 did hairstyling and manicure, so subtract that 33 from the 96, you will get 63. So if you add these two up, you will get the total number of hairstyling. If you add these two up, you will get the total number of manicure as given in the question. Now, the question is asking the customers who did hairstyling or manicure. That means probability that a customer had a hairstyling or a manicure. Just by looking at the Venn diagram, I can simply say because it's all this whole area divided by the total is the probability. From the Venn diagram, I can easily conclude that it will be 63 plus 33 plus 28 divided by 160, which will give me 31 over 40, 0.775. All right, I add these three numbers. Okay, and that will be my final answer. But if I want to represent it using the general method that we learned, the formula, which is probability of hairstyling plus probability of manicure minus probability of hairstyling and manicure. Okay, so probability of hairstyling was total how many? Hairstyling probability total were 96, manicure total were 61, minus the common, that is the 33. So you get again 31 over 40, which is 0.775. That means 77.5% of the customers had manicure or hairstyling. All right. So I think this question is clear now. Let's go for example 4. But before that, recall that from lesson 11.2 that complement of an event, sorry, it's 7.2, not 11. 7. Complement of an event with probability, supposed to be 7 here. All outcomes that are not in the event. So complement of an event with probability P are all the outcomes that are not in the event has a probability of 1 minus P. Okay, the complement of an event with probability P. That means we learned like something like this. Probability of the event E is equal to 1 minus probability of not E. Learned this formula before. We can use this to find probabilities of some compound events as well. So each of 6 students randomly choose a butterfly from a list of 8 types. What is the probability that at least 2 students choose the same butterfly? So the question is very clear. There were 6 students who are randomly choosing butterflies from a list. In the list, there were 8 types of butterflies. What is the probability that at least 2 students choose the same? So at least 2 students choose the same means the complement would be everyone is choosing different. At least 2 means they are saying like either 2 students or 3 students, 4 students. At least 2 means 2 or more. But to do that, it will be a bit complicated, so we do the opposite. So at least two choose same. The opposite of that would be everyone chooses different. So I can use the method of complement here. Okay, so you see here, use the complement. Probability of at least two choose the same is equal to 1 minus probability of all choose different. So all the students choose different. So 1 minus that, because 1 is our total probability of an event. Now, I mean, not of an event, when we sum up all the events in that experiment. Anyhow, let's continue. So what is the probability of all choose different? So since we are doing selection here, okay, so 6 students are choosing from 8 types, right? So this is a permutation based question. Why is it permutation based? Because order is important here. If when you are doing all choose different means when the first student is choosing, he has 8 options. When the second student starts to choose, he only has 7 options. Then the next one will have 6, then 5, then 4, then 3. All right, so these are the 6 students: 1, 2, 3, 4, 5, 6. Okay, so these are the number of ways the students can choose. 6 students can choose from 8 times. But this represents something. We already studied this thing. What is this? This is 8p6, right? And the total number of arrangements possible. So there are 6 students, and total means same or different, not a problem. Okay, so this is for everyone choosing different, but the total means doesn't matter they are choosing same or different. So every student would have 8 choices: 1, 2, 3, 4, 5, 6. So this is the total, which is 8 power 6, right? Then we'll calculate the answer. Let's put the answer from here. Probability of all choose different is number of ways 6 students can choose different butterflies divided by total number of ways 6 students can choose butterflies. So if you see here, it says 6 students can choose butterflies. So here they did not say about the importance of order, because he in this case there is no problem in repetition. So we use the fundamental principle, counting principle, if you remember. This is not, we cannot use the permutation formula for this, because repetition is allowed in this case. So 2 students can have the same also. So everything is included here. Same, different, doesn't matter in total. This is because it is total. Here it's a given case, or choose different. So here it is given choose different, but here it's not. Total means everything included. So for that we have this way, right? And this is the probability of at least 2 students choose same means 1 minus probability of all choose different. So 1 minus this, which is 0.9231. And that's about it. So it is 92.31 or 31%. Thank you for listening.